At first glance, this question is like identical to the last question. We're asked for the de Broglie wavelength. De Broglie wavelength is h over momentum. Momentum's m times v. We're given the m, we're given the v. It's just a matter of cranking it out. I'll plug down the numbers. H is the constant. We have to put the mass into kilograms, so that's 0.14. The speed is 450. If you've got the time, check out Smarter Every Day. Check out Destin's video. It's a fairly new one about, I think it was made in 2020. He shot a baseball, literally broke the speed of sound. Some cool physics and engineering you had to do to make that happen. When we crank it out, we get a wavelength of roughly 1 times 10 to the negative 35 meters. In the last question, when we were dealing with the electron, we got a wavelength that was 10 to the negative 11, which was crazy small, but not crazy small compared to the electron. This question, with a macroscopic object with something as huge as a baseball, we're getting an impossibly small wavelength. There's no way a baseball would ever be able to interact with something that's 10 to the negative 35 meters in size. The baseball is infinitely larger than that. Since the scale between the size of the baseball and the size of that wavelength is so ridiculously out of whack, we're not going to see any quantum effects of baseballs. We're not going to see like a double slit experiment with baseballs because we need the baseballs to interact with a d value on the order of 10 to the negative 35. And 10 to the negative 35 is impossibly small compared to the size of a baseball. So since this wavelength is ridiculously small compared to the baseball, we don't see the quantum effect of a baseball. As opposed to the last question with an electron, we got a small wavelength, but electrons are in the order or approximately the same size as that, so they could interact, and we can see the quantum effect of electrons.